Hello friends, welcome to the tutorial series on network analysis made simple. In this tutorial, we shall discuss the relations between the resonance frequency and half power frequencies. Friends, I have arrived at deciding the content of this tutorial by taking inputs from various university examination papers. Sometimes you are required to derive the expressions or use the appropriate equations to find the unknown. Therefore, in this tutorial, we shall first derive the relation between resonance frequency and half power frequencies. Then, we shall derive to show that the resonance frequency is an arithmetic mean of half power frequencies. Next, we shall derive the relation between half power frequencies in terms of bandwidth and half power frequencies in terms of quality factor Q and the resonance frequency. Finally, we shall derive the equation for the impedance in terms of the frequency deviation delta. So friends, first we shall derive the relation between the resonance frequency and half power frequencies. We know that at half power frequencies f1 and f2 or omega 1 and omega 2, mod of z1 is equal to mod of z2. At f1 and omega 1, xc is greater than xl. Therefore, mod of z is equal to square root of r square plus into bracket 1 upon omega 1c minus omega 1l whole square. Similarly, at f2 and omega 2, xl is greater than xc and mod of z is equal to square root of r squared plus into bracket omega 2l minus 1 upon omega 2c whole square. By equating the right hand sides of both equations, we get this equation, and by removing the square root, we get this equation. Friends, the equation obtained by equating the right hand sides is reproduced here. We see that r square cancels out and we get this equation. By removing the square, we get this equation. By rearranging, we get 1 upon omega 1 into omega 2 is equal to LC, or omega 1 into omega 2 is equal to 1 upon LC. But we know omega naught square is equal to 1 divided by LC. By substituting and solving, we get omega naught is equal to square root of omega 1 into omega 2 radians, or f naught is equal to square root of f1 into f2 hertz. It's very easy, isn't it? Friends, next we shall derive the equation to show that the resonance frequency is an arithmetic mean of half power frequency. Friends, the resonance frequency will be equal to the arithmetic mean of half power frequencies if Q is greater than or equal to 5. If so, R by 2L will be very much less than 1 by LC. And also we know omega 1 is equal to minus r by 2l plus square root of r by 2l whole square plus 1 by LC radians. And omega 2 is equal to r by 2l plus square root of r by 2l whole square plus 1 by LC radians. Hence, r by 2l can be neglected in both equations, so that we can write omega 1 is approximately equal to minus r by 2l plus 1 by root LC. And similarly, omega 2 is approximately equal to r by 2l plus 1 by root LC. By adding omega 1 and omega 2 and substituting for omega naught is equal to 1 divided by root LC and solving, we get omega naught is equal to omega 1 plus omega 2 divided by 2, which is the arithmetic mean of the half-hour frequencies. Friends, next we shall derive the relation between half-power frequencies in terms of bandwidth. We know that for a resonance circuit where Q is greater than 5, omega 1 is approximately equal to minus r by 2l plus 1 divided by square root of LC. And omega 2 is approximately equal to r by 2l plus 1 divided by root LC. We also know that bandwidth is equal to omega 2 minus omega 1 and is equal to r by L. And also we know omega naught is equal to 1 divided by root LC. By substituting for r by L and omega naught in the equations for omega 1 and omega 2 and solving, we get omega 1 is equal to minus into bracket omega 2 minus omega 1 divided by 2 plus omega naught, and omega 2 is equal to omega 2 minus omega 1 divided by 2 plus omega naught, or omega 1 is equal to omega naught minus bandwidth divided by 2 and omega 2 is equal to omega naught plus bandwidth divided by 2. Friends, remember these relations are true for the circuits where Q is greater than 5. Friends, now we shall derive the relation for half-power frequencies in terms of quality factor Q and resonance frequency omega naught. We know Q is equal to omega naught L by R and R by L is equal to omega naught by Q, and also omega naught square is equal to 1 divided by LC. We also know that omega 1 is equal to minus r by 2l plus square root of r by 2l whole square plus 1 by LC radians, and omega 2 is equal to r by 2l plus square root of r by 2l whole square plus 1 by LC radians. By substituting the values for r by L and 1 by LC as indicated in the equation for omega 1 and omega 2 and rearranging, we get omega 1 is equal to omega naught into bracket minus 1 by 2q plus square root of 1 by 2q whole square plus 1 radians, and omega 2 is equal to omega naught into bracket 1 by 2q plus square root of 1 by 2q whole square plus 1 radians. Friends, finally, we shall derive the expression for the impedance in terms of frequency deviation delta. Many a times, it is more important to analyze the response of a series resonant circuit in terms of frequency deviation. Frequency deviation delta is defined as the ratio of the difference between the operating frequencies and the resonant frequency expressed as a fraction of resonant frequency. Hence, delta is equal to omega minus omega naught divided by omega naught, where omega is the operating frequency in radians per second and omega naught is the resonant frequency in radians per second. Delta is positive if omega is greater than omega naught and delta is negative if omega is less than omega naught. We know that the impedance of a series resonant circuit Z is equal to R plus J into bracket omega L minus 1 upon omega C. Here, we assume that XL is greater than XC. By taking R outside, we get this equation wherein Z is equal to R into bracket 1 plus J into bracket omega L by R minus 1 divided by omega CR. By dividing the term in the bracket by omega naught both in the numerator and denominator, and by rearranging we get Z is equal to R into square bracket 1 plus J into bracket omega naught L by R into omega by omega naught minus 1 divided by omega naught CR into omega naught by omega. We know omega naught L by R is equal to 1 upon omega naught CR is equal to Q. By substituting and solving, we get Z is equal to R into square bracket 1 plus JQ into bracket omega by omega naught minus omega naught by omega. The equation obtained for Z is reproduced here for convenience. We know delta is equal to omega minus omega naught divided by omega naught, and it can be written as omega divided by omega naught minus 1. Omega by omega naught is equal to 1 plus delta. These relations we are going to use further. By substituting in the equation of Z and solving, we get Z is equal to R into square bracket 1 plus JQ into bracket 1 plus delta minus 1 divided by 1 plus delta. By solving it, we get Z is equal to R into square bracket 1 plus JQ delta into bracket 2 plus delta divided by 1 plus delta. If delta is very much less than 1, that is, if the operating frequency is very much close to the resonant frequency, then the equation for the impedance Z results in Z is equal to R into bracket 1 plus 2JQ delta. It may be noted that at resonance frequency, when delta is equal to 0, then Z is equal to R as usual. Friends, during this tutorial, we derived the relation between the resonant frequency and half-power frequencies. Then, we derived the expression to show that the resonance frequency is an arithmetic mean of half-power frequencies if Q is greater than 5. Next, we derived the relation between half-power frequencies in terms of bandwidth and half-power frequencies in terms of quality factor Q and the resonance frequency. Finally, we derived the equation for the impedance in terms of frequency deviation delta. Hope this presentation has kindled some of your thoughts. Please forward your feedback and suggestions to my email. Thank you for watching.